looking at the ultrastructure of the kidney. So first of all, this area here is the Bowman's or the renal capsule, which is where ultrafiltration takes place. This is the proximal convoluted tubule, where selective reabsorption takes place. This is the loop of Henle, where the reabsorption of water occurs. And this is the distal convoluted tubule, where the final little bits of absorption take place. And then this area here is the collecting duct, where the final last regulation of water takes place. So starting in the Bowman's capsule, that's where ultrafiltration occurs, and in essence that is where blood comes into the Bowman's capsule at high pressure in the afferent arteriole, and the afferent arteriole arrives and it goes into a capillary network. Okay, so obviously that increases the pressure. That is further increased by the fact that the vessel which takes the blood away is called the efferent, and that exits, and that has a smaller diameter than the afferent vessel. These factors increase the pressure. Add to that, the capillaries have what we call enlarged fenestrations, or they are leaky, and the membrane of the Bowman's capsule is specially adapted with podocyte cells to make filtration occur more easily. So the net effect of this is that substances are forced out of the glomerulus into the Bowman's capsule, and anything with a relative molecular mass of less than 69,000 leaves, and that basically means that the only things which stays are cells and proteins. So the first stage that all of this stuff goes through is the proximal convoluted tubule, and it is in here that something called selective reabsorption takes place. So this is a bit like if you're looking for your lucky pair of socks and you tip your entire sock drawer out on your bed and then you just pick out your lucky pair of socks. But in this case, 85% of the filtrate is reabsorbed, and it's done in the following way. So in this diagram, what we've got is here is the blood capillaries. This is the wall of the proximal convoluted tubule, and here is the lumen of the PCT, which is obviously where everything is. So actually the first thing that happens here, and what happens is that sodium ions are pumped that way and potassium ions are pumped this way, and this is an active process. Okay, so that is an active process, and the energy comes from the mitochondria, which are prevalent in these cells. What that does is it causes a lower concentration of sodium here, so then sodium enters by diffusion from the proximal convoluted tubule and brings with it glucose and amino acids. Okay, and what they can then do is they then continue on their journey into the bloodstream. You will notice that the cells are lined with microvilli. That obviously increases the surface area for absorption, and it is through this process, driven by an active process here and a passive process here, that the majority of substances that the blood requires are reabsorbed in the proximal convoluted tubule. The filtrate then moves on to the loop of Henle, and it is here that the majority of the water is reabsorbed. In the loop of Henle, you have the descending limb and the ascending limb. The descending limb is permeable to water, which, as you can see, I have coloured in blue, and the ascending limb is impermeable to water. Okay, so what happens here is that sodium and chloride ions are pumped out actively. Okay, so that is the active process there, and what that does is it increases the concentration of sodium and chloride ions here, which means that water will passively move into the interstitial space. What that does in turn is it lowers the water potential here, so water is more likely to continue to move out here. So when you get down here, you have a very, very high concentration of the solutes of the dissolved ions, which then means that sodium and chloride will move out by diffusion in this part and continue up here when they're then actively transported out to maintain this balance and this process. In the distal convoluted tubule, there is a last part of reabsorption that occurs, and that operates in much the same way as the proximal convoluted tubule. It's kind of like the final check. And then the very last thing that happens is that the filtrate moves through the collecting duct. Now, it is in the collecting duct that we have the very last regulation of water concentration. That's the only thing that can move at this point. And this is controlled by a hormone called ADH. Okay? ADH stands for anti-diuretic hormone. A diuretic is something which makes you want to urinate. So when ADH is released, it is trying to hold on to water. Okay? So if the osmoreceptors in the brain detect a low concentration of water in the blood, then a message will be sent to the pituitary glands to secrete the ADH. The ADH acts on the walls of the collecting duct to try and make them more permeable to water, so that water will leave the collecting duct, resulting in more concentrated urine and more water in the blood. And then the reverse is true. If the osmoreceptors in the brain detect that there is a high concentration of water in the bloodstream, then no ADH will be released. The walls of the collecting duct will remain impermeable to water. We'll have a high volume of dilute urine.